In this video, we get ourselves set up for using automatic differentiation within a machine learning loop by discussing how to represent an equation as a tensor graph, and then creating that graph in PyTorch. All right, so let's fit a simple line, the simplest possible line, with a machine learning model. To do that, we are going to represent the very simple line equation y equals mx plus b, where m is the slope of the line and b is the y-intercept. We're going to represent that line equation as a directed acyclic graph, also known as a DAG, or abbreviated as a DAG. We will talk about DAGs in much more detail in the algorithms and data structures subject of this Machine Learning Foundation series, which is coming up. It's subject 7 of 8 in the series. For now, we're just going to quickly talk about it. So the graph, the directed acyclic graph for our line equation, consists of nodes. So each of these points in the graph is a node. 1, 2, 3, 4, 5, 6 nodes. And we have an input node, which is x. We have an output node, which is y. And we have our parameters, both shown in green, the slope m and the y-intercept b. We also have operations acting as nodes. So we have the multiplication operation, where we'll multiply m times x. And then we have this addition operation, which will add b to the product of m times x. All right, so those are our nodes, what we call nodes. Another aspect of a graph in graph theory is that we have edges that connect the nodes. So in this case, we have 1, 2, 3, 4, 5 edges. And these are directed edges because they flow in a particular direction. So you could have undirected edges, which wouldn't be an arrow at all, or you could also have edges that go in both directions. In this case, we have edges that only go in one direction, and the graph as a whole has no cycles, it has no loops. So it is a directed, because it has direction, acyclic, because it has no loops, and a graph because, well, we're representing it as a graph of these tensors. So each of these directed edges are tensors that hold some information. So here it holds the information about x, here it holds for m, and then here it's a tensor that carries the product of m times x to this addition node, and then there's this tensor here that holds b, and then finally we have a tensor that gives us our output y. All right, so now that we have our DAG representing our simple line equation, let's jump into a hands-on code demo in the Regression in PyTorch notebook in order to create this DAG of our simple line equation in PyTorch. Okay, so heading to our trusty code repository for the Machine Learning Foundations series at github.com/Jon Krohn/ML Foundations. In this subject, we've been working through the Calculus 1 notebook, but in fact, if you go have a look at that notebook, we've now reached the end of the notebook, which provides a link to this standalone Regression in PyTorch notebook. And we have it standing alone so that we can use it again, actually, in subject 4, the second calculus subject. So we will be returning to that notebook again in this subject when we'll be examining it through a different lens. But anyway, we're still in Calculus 1 right now. So you can either click through to the notebook here at the bottom of the Calculus 1 notebook, or you can go into the notebook's directory of the repository, and you can find the Regression in PyTorch notebook in there. Either way, when you make your way to it, you can either follow along statically, as you are able to for any of the notebooks in this GitHub repository, but I recommend that you open it up in Colab so that you can execute the code alongside me. So as always, when we get started in Colab, we want to go up to Edit and Clear All Outputs so that all the outputs that I did provide for the people who are choosing to view statically in GitHub are removed. And then we can get started. So in this notebook, we are going to use automatic differentiation in the PyTorch library to fit a straight line to data points. So using the line equation from the slides to fit some data points. So here we are going to use calculus to solve the same regression problem that we used the Moore-Penrose pseudo-inverse to solve totally algebraically in the Linear Algebra 2 subject notebook. So you can go back and have a look at that, but we're going to be using the same data points again here and using a completely different approach to fit a line. So we start off by importing PyTorch as well as Matplotlib for creating some plots. And we are going to use up some made up data that, as I said, the same data that I made up for this Linear Algebra 2 notebook. So our x values, our inputs into the line equation, are going to be these values that are supposed to represent the dosage of a drug for treating Alzheimer's disease. So again, I made this up, but the y values were created using the equation of a line. So we used the line equation y equals mx plus b to create the y values. And by doing this, we know what the underlying model parameters to be learned should be. So I used this slope of negative 0.5 and this y-intercept of 2. So I used this formula right here, this cell of code, which has that m times x, so our slope times our x inputs, plus our y-intercept of 2. And then I added random normally distributed noise. And this allows us to simulate a sampling error, because in the real world, most processes, and certainly all biological processes, like this made-up Alzheimer's drug example, we wouldn't have a perfect relationship between x and y. There would be some random noise associated with our observations. And so we're going to learn a lot more about probability distributions, including the normal distribution, as well as a lot more about random processes in subject 5 of the Machine Learning Foundation series, which is on probability theory. But for now, you can kind of just trust me that this method here works to add a little bit of reasonable noise. And so we have this argument here that we set to 0 so that our noise is distributed evenly around our line here. And then this argument here is how much noise. So this is the standard deviation of the noise. Again, that's a term that we won't cover in detail until subject 5, but it allows us to have differing amounts of noise. So if you were to make this number larger for this standard deviation argument, you would add more noise. If you brought it down to 0, then you would have no noise whatsoever, and you would just be fitting the line. You might as well not include this noise method at all. All right, so I'm not actually going to run this right now. At home, you're welcome to play around with the slope argument, the y-intercept argument. You're welcome to play around with how much noise there is, but I'm actually not going to run this code because I'm going to use some y values that I already created earlier using this function. So this way, for the reproducibility of this demo, so that you and I have the exact same y values, and every time you or I run this notebook, we have the exact same y values. I'm just going to use these fixed y values, but again, you're welcome to create y values instead. Of course, if you create your own y values using this line of code, then be sure to comment out this line of code so you don't overwrite these fixed values that we're going to stick with. So following along with my made-up Alzheimer's disease example, where our input into the model is the dosage of a drug that we have developed for treating Alzheimer's, say, and then the outcome that we're measuring, the output of our model, is the patient's forgetfulness. So let's have a look at the relationship between x and y by plotting them out. So we're plotting a scatter plot here with our drug dosage along the x-axis, and our patient's forgetfulness, these y values, now along the y-axis. And I've added some labels so that it's easy to keep track. But as we can see, there is a clear negative relationship between these two variables. So as we increase the drug dosage of our made-up Alzheimer's drug, we see that our patient's forgetfulness goes down. So this is the exact same data, and we created the exact same plot in that earlier Linear Algebra 2 subject notebook, but here it is again. So that's where the commonalities between the algebra notebook and our calculus approach here end. Because for our calculus approach here, we are going to solve the problem in a completely different way. We're going to use machine learning ultimately with calculus at the core, allowing us to differentiate and figure out how to fit a line to these data points. So, en route to doing that, en route to following the machine learning approach to fitting a line to these data points, we need to initialize our variables, our parameters for the line, with some random values. So that's a common thing that we do in machine learning. It feels a bit weird if you don't come from a machine learning background, but it's very, very common in machine learning models, from the simplest kind of models like regression models, like fitting a line to data points like we are today, all the way through to the most complex regression models like deep learning models. In all of those, the standard is to initialize your parameters, your model parameters, with random near zero values at the start. And as you get to approaches like deep learning, there are relatively sophisticated approaches for selecting random values from a specific distribution that is specific to different parts of your deep learning algorithm. But for our purposes here, for fitting this simple regression model, you could pick any near zero value as your starting point. And so I'm starting with this quote unquote random value of 0.9. That's a value that's pretty close to zero, so that it fits our criteria for picking a random initial value for our parameters. Now, you might ask yourself, well, look at this. We can see that there's a negative slope. So why don't we start with a value, a negative value that maybe approximates this here? And well, the answer is that I don't want to cheat like that. So in this simple demo, where we just have two variables and we're fitting a line to the points represented by those two variables, we could guess an approximately correct parameter value to start with. So we could pick a slope value that's approximately this slope. We could pick a y-intercept that is very close to 2. We can see that there would be a line here that would intercept around 2 on the y-axis. So we could guess approximately correct parameter values to start with. Or, like we did in the Linear Algebra 2 subject that was earlier in this Machine Learning Foundation series, we could use the Moore-Penrose pseudo-inverse to solve this problem. Or we could use a statistical approach. For example, we could use ordinary least squares regression to fit a line to these data points. And that's something that we'll cover in subject 6 of this Machine Learning Foundation series on statistics. And that would, for this simple problem, solve for the parameters very quickly. Indeed, it would. However, everything that we're doing here, this tiny machine learning demo that we're doing in this notebook, this Regression and PyTorch notebook, with just 2 parameters, m and b, so the slope and y-intercept, and just 8 data points, this approach that we're doing in a very small scale here scales to models that have millions of parameters instead of just 2, and millions of data points or billions of data points. I mean, it's true, billions of parameters too. I mean, this approach that we're introducing in this notebook, this machine learning approach, scales to any size of model, any amount of data. Whereas the other approaches that we talked about just now, guessing what the parameters should be, or linear algebra or statistics, they do not come close to scaling in this way. Anyway, that was a long-winded way to justify my use of this random 0.9 value for our slope as our starting point. You can pick another random value near 0. You could pick 0 itself or 0.1 or 0.001 or whatever. Just As long as it's not too big of a number, the bigger the number gets, you might make it impossible for your machine learning model to fit. But as long as it's a relatively near zero value, your model should make its way to a correct answer, to a well-fitting line for the data points. If you do want to get the exact same outputs as me as you're running through this, especially maybe the first time you're running through this notebook, I recommend leaving it at the same value as I'm using. And as we saw when we learned how to perform automatic differentiation in PyTorch, we use this requires grad method on our scalar tensor here to set the requires grad argument to true. And so this means that now when we use our x values and we flow them through a function, any of the other tensors that this M tensor comes into contact with will also track gradients, and this will allow us to perform differentiation back from our outcome, from our y variable in our line model. And so we'll be able to find the slope of y with respect to M and also with respect to B, because when we initialize our y-intercept for the parameter B, we're also going to require the gradient tracking. And again, here I'm picking another near zero value, a quote unquote random value of 0.1. I did deliberately, when I picked these supposedly random values, I picked ones where I knew that the model was going to have to do some work. So as I mentioned, you can see that the y-intercept is about 2. And so I picked a y-intercept that is close to 0, very, very close to 0, as opposed to being close to 2. And you can see visually that we have a negative slope. So I could have provided a negative slope for M to make our life very easy for our machine learning model, but I didn't want to make it too easy. I wanted you to be able to see the model learning and improving over time. And so I picked a positive slope, knowing that, we'd be able to see our slope change from positive to negative and gradually fit the data points. Okay, so I created this regression plot function, which I'm not going to dig into the detail on. You can do that on your own time. Essentially, what we're doing here is we are passing in all of our relevant variables, so our x values, our y values, our parameters M and B, and then we're plotting x and y against each other, just as we did here. But now we're also going to use this code here to fit a line to the data based on the M and B parameters that we have at any given time point. So here, when we've randomly initialized M and B with these values that we know don't fit the data very well, when we fit a line to it, following this code here, the line doesn't fit very well. Obviously, the line does not fit the data very well. So what we're going to learn next is how to fit this line to the data using machine learning. The last step in this notebook before learning a little bit more about that machine learning process is to have a method that actually allows us to take all of the components of our graph. So remember, we have this computational graph. Well, we have our x values, we have our y values. We initialize these at the top of the Jupyter Notebook. And then most recently in the Jupyter Notebook, we initialized our parameters with some quote unquote random starting values. So we have all of the components of our graph, and now we can link them together with this equation here, with this regression method that I created, which takes M and X and B. So it takes our parameters, it takes our input, and it multiplies M times X, adds B, which will give us Y. So there we've queued everything up. In the next video, we'll jump back to the slides, learn a little bit more machine learning theory, and then we'll come back right into this regression in PyTorch notebook and use that machine learning theory to actually fit this line to the data points thanks to automatic differentiation. To be sure not to miss the next video in this series, subscribe to my channel. Thanks for taking part in this tutorial. I hope you enjoyed it. If you did, please like and comment. To be sure not to miss any of my content, head to jonkrohn.com and sign up for my email newsletter. You're also welcome to add me on LinkedIn. Simply mention that you're a viewer of the Machine Learning Foundation series. And finally, you can follow me on Twitter too if that's your social medium of choice.